Welcome to the Physics Department Colloquium. And today it's my great pleasure to have Dr. Bruce Remington here to give us exciting talk about the NIF Discovery Science Program. Dr. Bruce Remington received his Bachelor of Science degree from Northern Michigan University in 1975 and his PhD degree in experimental heavy ion nuclear physics from Michigan State University in 1986. He held a postdoctoral appointment in the physics directorate at Lawrence Livermore National Laboratory, working on nuclear modeling and simulations of pre-equilibrium reactions. He then joined the laser program, which is now known as the National Ignition Facility Directorate at Livermore, in 1988. He has been a staff physicist in the inertial confinement fusion program and high energy density physics program since 1988. He was a group leader from 1996 to 2014 and a NIF Discovery Science Program leader from 2014 until present. He works on laser-driven high energy density hydrodynamics instabilities and mixing in a variety of settings, HED laboratory astrophysics, and solid-state dynamics at high pressure and strain rates. He has authored over 450 publications in the areas of nuclear physics, plasma physics, HED material science, hydrodynamics, and laboratory astrophysics. He is recipient of the APS DVP Excellence in Plasma Physics Award, now known as the Dawson Award, for his work on ablation front Rayleigh-Taylor instability. He is a fellow of the American Physical Society. He received the Edward Teller Medal in 2011 for pioneering research and leadership in inertial fusion science and applications. And he became the distinguished member of the technical staff at Livermore in 2012. He's the recipient of 2023 the Nobel Prize in Shock Physics, which recognizes outstanding contributions to understanding condensed matter and nonlinear physics through shock compression. Bruce is currently the program leader of the Discovery Science at NIF, which is a program that allows people from academia and the national lab to pursue basic science research using the NIF laser. Without further ado, let's welcome Dr. Remington.
Well, hello everybody, and thank you for coming to this presentation. So as described, I'll be talking about basic science on the NIF laser. So let's jump right in. Here's an outline. There's multiple pieces to this. So what I'll try to do is not talk in depth about any one topic, but try and go through, see if I can get through with shorter discussions of all 6 areas. So I'll talk a little bit about ICF, a little bit about discovery science in a broad sense, and then under discovery science, nuclear science, material science, hydrodynamics, and plasma physics. So, ICF at NIF, and these view graphs came from Dan Casey and David Schlossberg at Livermore. NIF is the world's most energetic laser with 192 beams and a total laser energy of 2.2 megajoules. This shows a picture of the laser in all its variations. You see 96 laser beams coming in from one side and 96 from the other, and they all enter into the chamber at the center on the right-hand side to generate the 2 megajoules we use for the experiments. Just to give a sense of scale, there's the same laser shown from the outside with 3 football fields put across it, showing the basic scale of the facility. Down there somewhere must be a few people walking around, but you can see the cars, so it gives you a sense of the size. On the inside, there's the target chamber on the left-hand side, showing half the beams coming in from the top and the other half of the beams coming in from the bottom. On the right-hand side is an image or a photo taken during the construction of NIF, showing a construction worker, two construction workers right up at the top trying to finish building the actual chamber so that we can then start putting in the equipment that makes it a laser facility. And the bottom right shows the target positioner and a diagnostic on the left-hand side, and then also an imaging diagnostic on the upper right-hand side for actually diagnosing the experiment. NIF ICF implosion spherical capsules are shown here. You can see on the lower left, in the middle left-hand side, you see a dime, and in the dime is a tiny little gray sphere that shows the size of the 1 millimeter diameter capsule that were used to start out the experiments. And on the upper right-hand side, we show the whole rum, the radiation cavity that goes around the capsule and provides the energy to implode it. You can see that on the upper right-hand side. And on the lower right-hand side, compared to the size of a human eye. Next, this shows a little bit more details about a typical capsule. All the capsules, individual capsules, are different, but this is a typical capsule. It's shown in the middle of the picture, and you can see the gray region, the thick gray region, called 80 microns. That's the ablator. HDC stands for high density carbon. That means diamond. So the ablator is made of diamond, which drives the pressure. And then below that is the cryogenic layer DT plasma or DT ice. And then below that is more ice without the dopant. And then this is all imploded. Okay, so here are, on the left-hand side is a 2D simulation of an actual implosion experiment, ICF implosion experiment. And you can see large perturbations from the surface roughness, and also from the tents that create big plasma jets that sweep down into the plasma and sort of take the spherical hotspot, which was supposed to be spherical, and make it rather distorted. And you can see it in the middle as the red region. So that's what happens from the mixing caused by the tent. The upper right-hand side shows the whole realm and shows how the tent is used to hold the capsule in the center of the whole realm. And so the tent is thin plastic that started out, I think, at 110 nanometer thickness tent, but quickly it was realized that large tent caused a lot of perturbations on the capsule implosion. That's shown on the lower right-hand side, where you see an X-ray radiograph of an ICF implosion at that time, and you see the big tent scar across the top and the bottom. So the perturbations caused by the tent itself, when the lasers come in, they interact with the inside of the whole room, the radiation cavity. They fill the cavity with radiation. It explodes the tent, and then the tent pushes against the capsule and creates these large perturbations. And so it's kind of funny that we were studying the 3D perturbations that are much smaller around the surface, and had been ignoring the tent. And so in some sense, we were ignoring the elephant in the room, right? If we're worried about perturbations, it's fine to worry about the 3D perturbations from the fine structure, but the tent is tearing the capsule apart into 3 pieces. So it's no wonder that the yields were below what were predicted with these kinds of perturbations present. And we didn't see them until we took an X-ray radiograph. So lots of times people tell me, well, at Livermore and probably at all of the national labs, we do a lot of work on large-scale simulations, radiation hydrodynamic simulations, molecular dynamic simulations. So simulations of all types, and a lot of effort put into them. But in the end, the experiments are what we're there for. And so this shows these perturbations at the time in the post-processing of the simulations were not predicted. So this was an experimental image, and we saw that in the middle of the night. We're thinking, oh my, this is going to kill all of the capsules we're planning to shoot. So we had to sort of stop and reconsider and try and get a solution to this. Well, the solution was to, let's see if I show that in the next one. More perturbations, this time with the fill tube. It doesn't show it. The solution was to go from a thicker tent, 110 nanometer thickness plastic, to 45 nanometer thickness plastic, which reduced the perturbations significantly so we could get better performance from the implosions. These are more simulations. These are now 3D simulations of NIF ICF implosions, showing basically the same information as the previous view graph, but including the tent, the fill tube. The fill tube. So what you do is you build the capsule, you put a very thin tube down into the capsule, and through that fill tube you inject the DT cryogenic liquid that wicks around the surface and then freezes into ice. So the fuel layer is ice DT, or DT ice, at a thickness of say 60 to 70 microns thick. And so the fluid is injected, the DT is injected as a fluid through the fill tube, and then it's frozen on the inner surface, and that's the fuel layer. And of course, the fill tube itself creates perturbations that jet across and distort the hot spot. So the whole trick of ICF is to try and minimize these distortions, but recognize that they're there and develop or design the experiment to be robust enough that the hot spot, which is at the core, ignites and burns before those perturbations jet down into the hot spot. You can't prevent them from jetting down in and getting there, but you can try and get the yield, the burning that you want done before that happens. And so that's the trick of how you balance all these effects and still get a burning plasma. Okay, this was a view graph that Dan Clark showed at a invited talk he gave at the HED conference a couple months ago. And he calls this inertial confinement fusion, rampant instabilities at pressures greater than 500 gigabar, and yet it burns, meaning basically what I said, you can't prevent the perturbations entirely, so you have to design a design that lets the burning that you want happen before those perturbations make it. So it's like a foot race. They're both there. One's coming in from somewhat of a distance. You got to get the other one done, get the burn out, and then once those perturbations from the fill tube and the tent get there, it's over. Okay, more about ICF. The left-hand side shows the whole rum, the tent holding the capsule, the lasers coming in. Above it on to the right is the laser pulse shape. It's sort of 8 nanoseconds long. You have an initial shock to begin with, and then a ramp up to a peak, and then the peak is held. And on the right-hand side is a whole series of experimental data points plotted in terms of the peak pressure of the implosion times the burn duration, tau, of the implosion. So the peak pressure means you can compress the hotspot to be higher density, and you want to have the highest density possible if you're trying to get the maximum fusion. And the time duration, of course, once you achieve those highest density, highest pressure conditions, you want to hold them there as long as you can to keep the burn burning. And so a typical burn duration is sort of between 50 to 70 picoseconds. And so if you can even get 5 more picoseconds out of that by finding ways to hold the plasma together before the rarefactions come in and release the pressure, then it pays off directly because the burning is there. It is burning. You just need to keep it burning. So that's sort of the challenge of designing ICF capsule implosions. On the upper right-hand side, you can see all the data points, and the data points off to the right of those blue curves all exceeded the ignition criteria. This is showing the same thing again with a bunch of fireworks notionally behind this, basically saying it worked. We started the ICF program, at least in the unclassified sense, in 1972. So it's a Nature article written by John Knuckles in 1972. So since 1972, we've been working on this. And so you can imagine when we finally achieved ignition, so many years later, it was worth a celebration. This is the same information showing fusion energy output as a function of time during, going through the whole series of, 20-some years of experiments. And the conclusion, image of what 5 megajoules looks like in the laboratory. So Dan Clark asks rhetorically, how can we use it? But I get rid of the rhetorically and say, well, you've asked a question. How can we use this? And so I'll give you an answer. I looked at astrophysics, and the closest thing in astrophysics to an ICF implosion is a type 1a supernova, what's called a thermonuclear supernova. So it's just a big version of that capsule implosion with the same physics going on. You generate perturbations. As you generate perturbations, the perturbations at the interface between the burning plasma and the non-burning plasma. There's perturbations at that interface, and when there's a larger perturbation, the surface area is larger, so the rate of burning goes up, which drives the perturbation to grow faster, which makes bigger perturbations, which surface area make that interface even larger, which increases the burn rate. So you have positive feedback between perturbations making the surface area of the unstable interface larger. That creates and increases the burn rate, which made it larger to begin with, so you get a positive feedback. And this is what is thought to cause the transition from a deflagration to a detonation. So a subsonic turbulent interface to a supersonic turbulent interface. That's the deflagration to detonation. That's what's that's the microphysics thought to be needed, thought to be happening in the type 1a supernova. And so when Dan Casey asked what can we use it for, I'd say this is what we should use it for. We should be trying to put this deflagration front analysis type into the experiments and the codes we're doing where we've actually demonstrated ignition and see whether or not these experiments and these large perturbations that we see in the burn front are related to this astrophysical instability. And if it is, it gives us a tie into type 1a physics, type 1a supernova physics. So Dan is working on this. I'll go consult with him when I get back to see how far we're getting along in this. And I think if it holds up that this is relevant to type 1a physics, then we should be doing more of this experiments on NIF discovery science. Because that's a big tick. You know, the type 1a supernovas are what they use to set the expansion rate of the universe. So it's a big ticket item if we could connect to that kind of physics with these NIF experiments. Okay, I'll say a few words about nuclear science. The upper left-hand side shows an implosion of a capsule where the fuel is the gas inside, and so driving the gas to high pressures and densities and getting the nuclear reactions to happen. So this on the upper right-hand side is plotted vertically is the stellar core density. Plotted horizontally is this stellar core temperature, K, ranging from 10 to the 7 to 10 to the 8 Kelvin. And so these plots are shown, in these plots relevant to the stellar age, are showing the experiments that we've done on NIF as the open circles. And so you can see how we've done a series of experiments of nuclear physics that is sensitive to electron screening and relevant to stellar interiors, how fusion reactions are happening at stellar cores. And the lower left-hand side shows the ion distribution at the same time as we plot the cross-section to show the region of overlap where the reactions are actually happening. And the bottom right-hand side is reactivity, which is the cross-section times the average velocity of the thermal plasma. And plotted here are the curves for TT reactions, tritium, hydrogen 3 plus hydrogen 3, or helium 3, hydrogen 3 times a triton, going to 2 alpha, 2n alpha, 2 neutrons and an alpha particle. More on nuclear physics, showing a lot more of what I just said, but on the upper right-hand side is a whole series of large-scale hydro simulations to span the parameter space that we think we might be able to get to. We're using this because Dan Casey wants to study nuclear physics where there's significant screening, meaning the density of electrons around these nuclei is high enough that it sort of screens the positive charge of the nuclei, so the two nuclei can get closer together before they realize there's two charged particles that want to repel. So it's a way of increasing the nuclear reaction rates by screening out the positive charge. And so with the densities that we can create on NIF, he thinks that we can increase the effective screening up to 20%. And he's pursuing that to see if we can make measurements that would back that up. Okay, so that's nuclear science. We'll now switch to material science, different topic. There's a planetary core in the center of Jupiter. Okay, so for the material science, we've been doing diffraction experiments on ramp compression of diamond, which is high density carbon, reaching 18 megabars on the NIF, and observed no phase transitions in time resolved diffraction experiments done on these implosions. And we've shown this for a duration of about 10 nanoseconds during the experiment. So we're able to hold the pressures for about 10 nanoseconds and make these measurements of the phases. In particular, we're trying to measure whether or not diamond, which starts out as FC8, I think it is, whether diamond goes through a phase transition at 10 to 15 megabars into the BC8 phase. So the BC8 phase is theoretically predicted by a large number of different code simulations and theoretical assessments. And so the diamond, when it's taken up to pressures above 10 megabars, is supposed to have a phase transition from FC8 to BC8 based on theory. Well, in experiments, diffraction experiments, we can measure what the phase is. And over the 10 nanosecond duration of these experiments, the diamond did not go through a phase transition. So the phase transition may be there, it's just going to take, you'll have to wait longer for it to happen, meaning the kinetics of the phase transition are slow because of the bond. Diamond has a very strong bond. Anyway, we're pursuing those experiments. On the lower right-hand side is the pulse shape of the different laser drives we're using to explore these regimes. You know, you think about this, we have to reach high pressures, maybe 20 megabars, maybe higher, but we have to keep the sample solid. So you're compressing a sample, but you can't go in and generate a bunch of shocks that'll get hot and cause it to change the liquid and plasma. We want to keep it solid. So it's a very careful ramp compression where we adjust the laser power versus time pulse shape very carefully so that we compress but don't melt. And we've gotten very good at that, and we do a lot of material science for that. This is a series. These are results from large-scale MD simulations by Ivan Olenik at University of South Florida. He has does large-scale code simulation predictions to try and understand why is it in the experiments we did, why is it we did not see the BC8 phase. And so theoretically, on this plot of temperature versus pressure, he plotted out where the BC8 transition should be based on very large-scale simulations that he thinks are capturing all of the relevant physics. And the conclusion is that the phase space where the BC8 is supposed to exist is pretty small in terms of the temperature and the pressure you have to get to. You can't just go in and hit it hard and hope you're going to pass through anything useful. You have to get to specific densities and temperatures and pressures to be able to see this BC8 transition. Ivan also had shots on NIF through the Discovery Science. And so in his last two shots, he thinks he has seen evidence that the final phase was different from the initial phase. He wouldn't say to me, predict that he'd actually seen BC8, but he said that he has good evidence that the final phase is no longer the starting phase, which was FC8. And so he left it there. But of course, everyone jumps on that and thinks he probably has seen BC8. But it's not published yet, so I'm going to ping him tonight to say, what's the time scale of getting the paper out, because people are interested. We also measured the melt curve. In terms of the material properties that might be the most useful to astrophysicists studying planetary physics would be the melt curve. Just consider the difference between FC8 and BC8 are there, but the difference between a solid and a liquid are much larger. So if you can't measure actual phases of the individual phases, at least try and measure where the melt curve is as a function of pressure. So Rick Krauss measured the melt curve of iron up to pressures of 1,000 GPa, which is 10 megabars, using time-resolved diffraction. And on the lower right-hand side, he plotted his results up in a plot of temperature versus pressure. And so he goes through and sort of maps out the melt curve very carefully, working by first melting the sample, then refreezing it, and measuring it, and measuring the temperature pressure conditions at the refrozen state. And so that he's mapped out the melt curve of iron. That's exceedingly valuable for the people who do planetary interior studies. Okay, so why stop at megabars? Laser energy, we still have enough laser energy to turn it up. So we've done measurements of the shock equation of state of C3H10 to near gigabar pressures. So we're working our way towards the gigabar regime to try and get to the highest pressures where we've ever done experimental work. And to be quick about this, you go to the bottom right-hand side, and that's a plot of pressure versus compression for a whole series of experiments going back to the Nova laser and then the Omega laser, and then the higher pressures starting at about 50 megabar. These are experiments done on the NIF laser in one campaign. And then a follow-up campaign pushed those energies up to about 700 megabar by Andrea Kritcher. So Tilo Depner did the first experiments at 60 megabars, and then Andrea Kritcher published the results up to 500 megabars. But backing up, Tilo wasn't super happy with the fact that he was down at the 60 megabar. I mean, there was a big negotiation on the team who would publish what and when. And so in the end of those discussions, Tilo was given the data to publish up to 60 megabars, and then Andrea Kritcher published on up to 500 to 700 megabars. Well, Tilo was not happy with that. So some 5 to 8 years, 7 years later, he came back this time and he said, I'm going to set the record straight. He used spherical beryllium shells to implode, and his goal was to get well into the gigabar regime, which he did. So he imploded beryllium shells up to 3 gigabars, which is 300 TPA, and then he used X-ray Thompson scattering to measure the temperature, the density, and the ionization state of the matter at those conditions. And that's shown on the upper right-hand side. You can see the raw data from X-ray Thompson scattering. So he did a really, really good job on these experiments and the analysis. And then working with an academic, Dirk Gericke from Warwick University in the UK, they produced this master plot on the bottom right, where you can see they've plotted temperature scaled by the K-shell ionization energy versus what I would call, roughly speaking, radius scaled by the separation of ions in a standard model of an atom. And so these are all in dimensionless terms. But what is nice is that he plots his data points on there as those 2 dark blue triangles, and then to the right of that, 2 red triangles. But he also put on the curves that correspond to a whole number of astrophysical phenomena, like the interior of the sun, the interior of Sirius B, which is a white dwarf star, the interior of Proxima Centauri, which I think is a red dwarf star, the interior of a brown dwarf called 229b, and he's got a plot there for that, and there's one more, which is Jupiter. So he put all these astrophysical phenomena that are of interest, at least to me they are, overlaid with the experimental data. And so it just gives you a really nice sense of the types of regimes we might think about trying to access and then do experiments at. So you say, I'm interested in this area of the universe. We work out what's the temperature and density there, then come back and say, could we reach those conditions? And if so, what kind of diagnostics do we have to try and study them? So that's nice. Okay, hydro instabilities and turbulence. So this is a simulation of type 1 supernova 1987A supernova explosion that happened in 1987A. Very nice, shows lots of hydrodynamic instabilities, Rayleigh-Taylor spikes and bubbles going on. And the instabilities actually affect the rates of these explosions, very much like the discussion I had about a Landau-Darius instability. The perturbations increase the surface area, which increases the rate of burning, and so on. This is a similar by a different author studying the same supernova with large-scale simulations showing the turbulence. So the fact that in supernova explosions, the fact that there's turbulence there, I think, is no longer disputed. It seems like a central piece of the supernova explosion. Well, it appears that we're not the only ones in the world, in history at least, interested in turbulent flows and mixing. So here's some sketches on paper by Leonardo da Vinci, going back to the year 1500. And if you want to read about these images are discussed in multiple references given down below at the bottom. And what did Leonardo call it? He called this an illustration of turbulent flows. He's not alone, though, in being interested in turbulence. Look at the Kelvin-Helmholtz instabilities in this sketch by Vincent van Gogh that he called The Starry Night. And so the references for this is also shown at the bottom if you wanted to read about it. I read about both of these in a physics of plasma paper by Yi Zhao in 2019. That's where the figures existed, and that's also where I learned about that, and then I got references from him. And so that's a lot of fun. All right, we already looked at this. Can ignition on NIFs lead to experimental studies of thermonuclear flame fronts? I hope the answer is yes. I'm going to try and pursue that a bit to push that along to see if it's possible. If it's possible, I'd like to know. And if it is possible, start the discussion. Should we do it, or how can we do it and actually enter into this in an experimental way? Okay, I think I'll skip this one. Okay, well, we've also done hydrodynamics with involving a radiative shock. So these are experiments by Carolyn Krantz at the University of Michigan. She wanted to study Rayleigh-Taylor instability growth in the linear to deep nonlinear regime in the presence of a radiative shock, because that happens often in astrophysics. There's plenty of explosions in astrophysics. The explosions are generally energetic enough that they generate a radiative shock, and then the radiation affects the rate of growth of the hydro instabilities. It lowers them. And so she wanted to study that process. She set up an experiment where a shock passed from a thick layer into a lower density layer. That leads to an unstable interface between the high density being decelerated by the low density. And if the low density layer is low enough, the shock can be a radiative shock, and so you can get radiative stabilization. So by controlling the strength of the shock, she could control a non-stabilized classical Rayleigh-Taylor instability in the same density and pressure regimes. But turning up the radiation level, she could then study the case where there's radiative shock stabilization that lowers the rate of growth of the instabilities. So that was a very nice result and a nice paper. Okay, one more, going to an extreme. This is one that I led. So everybody's having fun in the plasma regime. I said, why don't we study hydrodynamic instability flows like you think of in fluids, but let's change what is flowing and keep it solid. So this is an instability driven in lead. So this is lead being pushed into a much lower density, probably plastic, and creating a Rayleigh-Taylor unstable interface. But the lead is at high pressure, but is by design stayed solid. And so we have a solid material flowing like a liquid, but the strength presents itself like an extreme viscosity. It lowers the rate of growth of the ripples. And so we set up that interface, made the measurements, it worked. You can see on the bottom right-hand side, growth factor versus time. Growth factor means how much, if you put a pre-imposed ripple on and make it Rayleigh-Taylor unstable, how much did it grow? And so the fact that the data points are low compared to simulations says that there was significant strength due to the Rayleigh-Taylor instability happening in a solid state. So it's effectively like the viscosity is slowing down the rate of growth. So that experiment worked very well, and we published this in a PRL, I believe it was in. Going to the opposite regime in hydrodynamics, there's people interested in just the opposite of that. Typically in ICF, we're talking about lowering the growth rate because we don't want the perturbations. That experiment with solids also lowered the growth rate because it was the thing that I was interested in at that moment. There's the flip side, is just let them go and let them evolve quickly into turbulence and then deal with the turbulence, characterize it, measure it, probe it, see if you can use it. And so this group from Chicago, there was a bunch of us on the project, but the lead person was Bob Rosner and Don Lamb from the University of Chicago. And they had a postdoc, Jenna Meinecke, who was the person who actually came and did the experiment. But anyway, on the left-hand side, on the upper left hand, there's the actual experimental configuration. You have the lasers come in, they drive a flow to the right and left. The flow, when the flow collides, you have a chance to sort of create a specific amount of mix. And so by passing the flows first through a grid on each side, so the flow goes through a grid, so now it's little individual filaments, and you align the filaments to be not hit head on, but be, designed in between, so you don't have a head-on collision, but that maximizes the Kelvin-Helmholtz instability. So that's the fastest way to get the turbulence is to spin up the Kelvin-Helmholtz. So on the upper right-hand side are simulations showing that we think we've generated a turbulent plasma. We compared the simulations with the experiments, which are on the bottom right. And so this technique got us into a turbulent regime very quickly. And on the bottom right-hand side, one of the most interesting observations straight off was the following. On the bottom right image, you see little bright speckles. Well localized, but little bright speckles. Well, those speckles, where they're bright, means they're hot. So you have all these little speckle regions that are very hot, surrounded by a lower temperature plasma. And yet it's been there for 23 nanoseconds, which is a long time for a laser experiment. So then the question is, well, those little speckles should have cooled by thermal conduction. You put a hot wire in a water, for example, and turn off the source of heat, it's going to quickly cool. So the question is, why do these little localized tiny speckles not cool? Because they've been sitting there in a lower temperature plasma medium for 23 nanoseconds. So that was a bit of a head scratcher. And the conclusion was, we think the turbulence was large enough that the turbulence itself set up, these little turbulent flows set up their own magnetic fields, and it's the magnetic fields created by the turbulence that slows down the rate of heat conduction, because the heat conduction would be charged particles moving across those interfaces, and so you can reduce the heat flow by taking those little filaments and just sort of spinning them around by the magnetic field, which is the qualitative explanation why was the NIF experiment not turbulent with those speckles, and why the Omega experiment cooled itself like we sort of expected would happen. So that was fun. And I think I succeeded to go. This was led by the University of Chicago. And I just made a visit back there to the university and spent a day there to try and get them to come back and do a sequel to this. The experiment worked, but I think we could probe it and play with it and actually do some physics with the turbulence once we created it. So I'm hoping they will put in a proposal to do that. Next are shocks, plasma. This is going to plasma physics now. This is the last section. Shocks, well, you look up in the universe with telescopes and you see supernova remnants everywhere. And if you zoom in on any one supernova remnant, this happens to be what's called Tycho's supernova of 1572. So in the year 1572, the star exploded, and we're still studying and looking at the remnant of that explosion. But you see this beautiful outer edge that's nice and smooth. It looks kind of blue. That's the leading forward shock, and it's a collisionless shock. This is a shock that's occurring in a quasi-vacuum. And if you think about it, a shock is when you compress up matter, right? So if you launch a shock into a vacuum, there should be no shock. I mean, there's nothing to shock. So in outer space, collisionless shocks, based on that line of thinking, cannot happen. And yet you put a telescope out there, and there they are. So anytime you reach it in this area, in this field, anytime you reach a conundrum where there's just no way that this could happen, but there it is, you should suspect plasma physics and plasma instabilities. They're almost certainly the culprit. So plasma physics causes this collisionless shock front, and plasma instabilities cause the turbulence behind it. So these are nice results and very nice reading to go through. So anyway, how do we study that? Simplest way that we came up with is we have two planar foils of plastic. It was actually CD2, so we could get nuclear reactions from the DD collisions as a way to test the temperature. But in any case, you shine lasers on both sides, you generate a very fast, low-density flow coming towards each other. When those flows meet in the middle was 25, those foils were 25 millimeters apart. Now that's not much, for you and me, but 25 millimeters in a region where the experiments typically happen in 10 micron scales is huge. So they were way far apart. They launched plasma flow. The plasmas, when they finally collided, were low density because they had traveled so far. So the densities were low. And so what should happen are you generate a certain amount of turbulence, but there's no shock. But in reality, a shock was formed. And so the question is, well, how do we understand that? So we did a bunch of PIC simulations to support the experiments. And of course, we did a number of NIF experiments because it was a campaign. And on the upper left-hand side, you can see the experimental energy spectra from the electrons. And it shows electrons were accelerated all the way up to 500 keV energies by whatever plasma physics process led to the shock to form. It also created these energetic particles by the Fermi acceleration mechanism. So particle acceleration up to 500 keV, shocks where they were not supposed to be. They also generate their own magnetic fields. You see on the bottom side are magnetic field, and you see it's a kind of a turbulent, just as I described back here when I said, look in the middle of that and all that turbulence. All that turbulence is flowing, but they also generate their own little regions of magnetic field. That's what these simulations on the bottom are showing. So we have good simulation and theory support for very interesting physics and astrophysics for regions where we also have done experiments, showing on the top left. So we put that together. It was a very nice campaign. This one is also really nice. It has to do with magnetic reconnection. I think I'm running out of time, and this is very dense, so I'll just say that Will Fox and Vicente Valenzuela, who was or is his student, and he was at Princeton at the time he published this paper, studied magnetic reconnection on the NIF laser, simulated it, did theory for it. There's this physics of plasmas paper that Vicente wrote, and then Will Fox is writing I think he's writing a physical review letter. Just about done here. So using the arc laser, we can reach relativistic energies. So skipping sort of right to the end result of this. On the bottom right-hand side are a series of data plots plotting temperature versus laser intensity. So the temperatures we're creating with the arc laser in the plasma flows are reaching a few MeV. So we can reach MeV temperatures in electrons means relativistic plasmas. So we can generate relativistic plasma physics with the arc lasers. There's 4 of them. There's 4 beamlets. And we're doing that and using that both to characterize the plasmas, and hopefully, it hasn't started yet, but hopefully I'm going to generate interest in studying things like gamma ray bursts and using some of the experiments that we can do on the arc laser at NIF to bring in some gamma ray burst physics. So I'm hoping my big vision for the future would be some gamma ray burst physics with the arc laser and some type 1A, supernova type 1A physics for the long pulse high energy laser going forward. Some work on star formation dynamics motivated by Christoph Federath in Australia, where they study a lot of astrophysics. And this is from their group where they're plotting basically the variance of the density plotted up versus Mach number of the turbulent flow. And overplotted, all these symbols are astrophysical objects of one type or another that are of interest for people studying star formation rate. And showing right in the middle, while those 2 gray boxes were 2 experiments we did that were motivated by a Physics Today article written by Christoph Federath. We got together on the telephone. He was in Australia. We had a con call. We formed a little effort with some of our people, and it ultimately ended up in a successful Discovery Science project or a proposal that got accepted. So now they're actually shooting the laser, and the regions they have mapped into are shown by those squares. And so you can see how the squares fall in sort of this master plot of astrophysical objects and phenomena. So that's really cool, and it's happening, real time. And they're getting their first papers written. There's lots of publications coming out. I've come up with 36, I think it is, or something like that. Dan Calendar thinks we actually have about up to 90 papers, so I'm trying to actually come up with the final list. But there's plenty of material to read about if you have any interest. You can ask me to send you this one, or you can ask me to send you the Excel file that Dan created with everything on there. So with that, that's my conclusion. If you have any interest in this kind of science, you can talk to me at any time. Email works, text messaging works, telephone still works, calling me up, meeting me at the conferences. So I'm done. Thank you.
If you have any question, I will send a mic to you.
So you said a couple times that increasing the surface area of the interface between the burning and non-burning plasma increases the burn rate. Why is that?
Because what's burning, I mean, that interface is that's where the burning starts. And so if you make more interface for the same volume, you're going to get more burning. Just take and put it like putting side by side burning fronts, right? Here you got one, here you got two, you put them side by side, you got twice as much. The pulse duration for the NIF laser is typically from 1 nanosecond to 60 nanoseconds. I think there's a capability to go down to maybe 0.8 nanoseconds. But people are typically not doing that because we built the arc laser to sort of do the short pulse stuff. So the big long pulse laser is call it 1 to 100 nanoseconds, roughly.
I see. And is making it shorter an advantage? Or?
No, I mean, there was a time when we could shoot it at, I think it was 0.7 or something like that, but no one's doing that anymore, and I think maybe it was too much effort for the people setting up the experiments or something. Plus with the arc laser, we got a shorter pulse laser, so we use arc for that, typically.
And I was also wondering if the optics, any inclusion in the optics like lenses is a problem at those incredible powers?
Yes. I mean, the laser damage is real. So when we propose experiments, the proposals go to a number of different groups to give input on. First off is there's someone has to answer the question in a proposal, is the physics good? Usually that's good because usually we've thought about that. Then it goes to the target guys. Can you really build this target? So they have to say yes or no. There's the diagnostic people. They have to say yes or no. And there's anything else, like you were just bringing up these issues. Should we worry about that? And at that point, it has to get brought forward and discussed.
Mm-hmm.
The committee, they have the final word, but they want to know what they're giving their word on, right?
What's the repetition rate? How many shots can you do in a day?
3 at most. That assumes nothing breaks, but 3. 4 has been done, but it's like one diagnostic, and no one does experiments like that.
You mentioned NIF is the biggest facility in the world, but are there other facilities that can chase after some of the high energy density physics that you talked about?
Yes, France is in this, so they have facilities they have developed and are using in France, and China is jumping in, also Japan. For the big facilities, the nanosecond ones, actually Korea as well. So there's China, Japan, Korea, France, UK is in this, and then Livermore. Not Livermore, United States. Quite a good group of facilities.
So you showed that nice picture of the ignited plasma, and you mentioned that the capsule is 1 millimeter or 2 in diameter. What was the scale of the hot spots in that 5-lobed?
The scale of the hot spot
plasma
itself is maybe a diameter of 50 to 70 microns.
Okay, so in what are the densities of the DT that you can
Well,
get?
if it's an implosion hotspot, then the densities are very high, like 500 grams per cc. I mean, that's the whole essence of the implosion. You need to get the densities high, and the temperature's high enough to burn it, and that's how you get to the ignition and get the maximum yield. It's quite an achievement, when all is said and done.
Are there other questions?
Yeah, so the arc laser is has been around since like 2009, but is there a way to like extend the parameter space by improving like the diagnostics or other stuff that can like extend the capabilities of this of the laser in terms of the HEDP experiments?
Is this for the arc laser or the arc and the long pulse laser?
Yeah, just the overall setup.
Well, we're in the middle of what's called, or not in the middle, we're in the beginning of what's called a sustainment effort. Well, the sustainment effort is to stop doing shots for us and go sort of fix any problems that have accumulated over the last 20 years of using NIF. And so they have to stop doing experiments and look and see and fix. So we are doing that. Maybe the experimentalists like me are maybe not so happy about it because the experiments are being turned down to either low or even zero for a while to let the people go in and work on the laser, to try and clean up things where they can, fix anything that needs to be fixed.
Does that mean there will be an upgrade of the laser in terms of parameters?
And an upgrade is directly after the sustainment. There's also supposed to be an upgrade to take it from 2.2 megajoules to 2.4 maybe something. It's not a lot, but it's a little. And if you do a little, it means you could do a little again, maybe sometime. So there's attempts to push the energy up and certainly fix anything that's been, needs fixing after having used it for 20 years. It's a big deal because you're shutting down our research. Basically, for people like me, you're basically shutting down my research for some extended period. So you can imagine we pushed back on that for quite some time.
So you discussed this interesting problem where you have a shock at a vacuum interface, and in a plasma, the ions, the electrons will run ahead and then accelerate the ions, and then you get an expansion at the acoustic speed. And I wonder if that is what's seen in observation. Well, sort of an expanding slab type of problem. I don't know.
We certainly measured the shock itself, but then there's the part that it was launched out of, and it's an expanding plasma, so it may have the physics you're talking about in it. The focus has been on the shock because it's sort of the low-hanging fruit, but there might be something in the denser region that that is relevant to what you said.
Yeah, the plasma or the material would expand at the sound speed of the ion.
So if we could find a way to measure the sound speed as a function of how it sort of the density drops and expands out, you're saying that could be useful.
Yeah,
scientifically. Well, that's good to hear. Thank you. Maybe someone's thought about it. I haven't.
Are there other questions around? Maybe let me ask one question. So what would it take somebody here to do discovery science and NIF if they're interested in
I'm glad you asked. Normally I'm supposed to ask things like that, but if I get tired by the end of the talk, I just sort of stop. The thing to do is to first off, contact someone and talk with them. Now, that somebody could be me, but it could be anyone that you know, especially anyone you know at Livermore who's involved with discovery science. You can just talk to them. What's the process? How would a person like me sitting here at the university, away from Livermore or the national labs, how could we even think about starting something? Well, it's not that hard. You make a phone call to me or someone like me at Livermore or at Los Alamos or Omega, and start a conversation. How do you come up with experiments, and then how do you go through the process of getting them vetted and in the mix for possible acceptance? It's all worked out. The simplest thing I do usually is I say, send me an email saying you want some further information, and I'll send you back an email of the wide email announcements that are sent out for how you get laser time. And you read that, and it spells it out, point by point. And after that, we can take questions and answer, what does this mean? How do we do that? And so that's easy. An email to me, and I send an email back to you, and within 5 minutes, you've got information in your inbox.
That's great. Everybody should be doing that.
You should. And if I don't answer once, send it again. I get a lot of emails, and also, if I'm working on something, there's times when I simply shut down everything else, much to the chagrin of everyone else. But I just say, I'm going to work on something for this day and not be bothered, and I kind of shut down the rest. But I don't do that very often.
Okay, are there other questions? So if not, let's thank the speaker again. And for those of you who are joining us for dinner, we can meet in the front.
Oh, I did, didn't I?
Yeah.
You get better at talking faster or being selective what I say. Oh, yes. By all means.
Yeah, yeah.